Hey everybody, today I'm going to show you the way we deal with weak acid titrations. What I'm going to do is going to show you the basics of a weak acid strong base titration. So what I'm going to do is I'm going to have a weak acid being titrated with a strong base. So the general idea is that you're going to have in that burette, you're going to have your sodium hydroxide, okay, and that's your titrant. And at the bottom, what you're going to have in a flask or a beaker is you're going to have your weak acid. Okay, so we're going to titrate this weak acid, which will be considered the analyte, with this titrant, which is going to be our strong base. Okay, so what we're going to do is we're going to calculate the pH of this solution down here as we add more and more of the base. So we're going to be looking at pH changes as we add sodium hydroxide. So we'll be looking at a graph that will look something like this when we're finished. So what I'm going to do is I'm going to do a number of points. I'm going to show you the 0 point. I'm going to show you the 10 milliliters, 25, 50, and 60 milliliters. So we're going to add sodium hydroxide down here, and this is going to be in milliliters. We're going to look at how the pH changes. Now this is a typical curve for a pH, okay, for a titration curve. You typically see this S-shaped curve. I'm going to talk about all the features of this and explain why we see what we see as we go through these points. Okay, so I'm going to go one by one. I'm going to break this up into a couple videos and show you a number of parts. All right, so first of all, let's start with adding 0 milliliters of the base. So what I'm doing is I'm not adding any base. All I have right now is just my weak acid. So I'm going to start with part A, and what I want to do is I want to list the major species that I have present. What do I have in the solution right now? Well, right now all I have is my weak acid. My acetic acid is the only thing in here. By the way, to save some time, I'm going to write HA. I'm going to call this the acetic acid will be HA. And then A minus will be the C2H3 O2 anions. Save some time on writing. And you can do this in your homework and stuff as well. And even on tests, if you've got like a long molecule and stuff, if you want to make an abbreviation like that, by all means do it. Okay, so what I have in here is I have my weak acid and I have H2O. I really don't have anything else in here. Remember, the weak acid doesn't dissociate much. I haven't added any of the base yet, so all I have in there is 50 milliliters of the 0.1 molar solution of acetic acid. All right, so all I have at this point is just a regular weak acid problem. Typical weak acid equilibrium. So I'm going to do is just take my weak acid, HA, and I'm going to go ahead and set up the equilibrium expression. Okay, so what I did here is a typical weak acid problem that we've seen before, okay, where I have the weak acid dissociating and plug everything in. It follows the same pattern that we did in the last unit, where we just solve for the x, making sure we take the square of this and take the square root of it after we do the multiplication. Anyway, I end up with a pH of 2.88. So if I go to my chart, my pH initially here is going to start out as 2.88. So I start down here at the bottom. So this point here on my graph is going to be a 2.88 pH. Okay, so I start out low because I have an acid and that's all I have in solution. So now what I'm going to do is I'm going to add the base, and as I add the base, I should get my pH to go up. But notice it doesn't go up at a, in a linear fashion. It goes up in this more of a strange fashion that it's doing. So let's take a look at why that is. All right, so what I'm going to do is I'm going to set up the next problem. Okay, so what I do is I just chop things up a little bit here so we can kind of focus a little bit more on what's going on. So I'm going to do part B. For part B, I want to list the major species that I have present. Well, at this point in the reaction, what I've done is I've added 10 milliliters of the sodium hydroxide. Now I'm going back to square one. Well, obviously I'm still at square one because I haven't added anything yet. So now I have the sodium hydroxide and the weak acid together in the solution. So what do I have? I have HA. Remember, I'm doing HA as my acid. And I also have sodium ions. And I have hydroxide ions in solution. And I also have water. Okay, now sodium hydroxide dissociates completely. That's why I'm writing it in ion form. Remember, the three things that you write in ion form are the strong acids, strong bases, and ionic compounds that dissolve. Okay, so when I'm looking at this and I'm analyzing this, what I have is a weak acid. Sodium ions do nothing. Strong base. And then, of course, water, which is neutral. So what happens is if I have a base and an acid together, they react with each other. So that's what I'm going to do first. I'm going to do that step first. I'm going to do the reaction between the weak acid and the OH minus. You could throw the sodium in here if you want, it's up to you, but you don't really need it because the sodium ion isn't doing anything. It's a spectator ion, and it's not going to have any effect on the reaction. And what we do is start with the BCA table. All right, now what I need to do is I need to figure out how many moles that I have, because remember we deal with ice table or BCA tables. What I'm going to do is plug moles in here. So you can use the volume and the molarity to find the moles of the acid that you have. And when you do that, you're going to end up with 0.0050 moles of the weak acid. We can use the volume and the molarity. Remember, volume times molarity gives you moles. So if I take that volume, converting it to liters, and molarity, I can find out that I have 0.001 moles of the strong acid, strong base. This we don't care about, and this starts out at 0 because I don't have any of those anions yet in solution. So I do the stoichiometry here, minus x plus x. Now in this reaction, because I'm doing a BCA table, I'm always going to have a limiting reactant. Now how do I know that I'm doing this? Because anytime you have strong acids or strong bases that you're adding, you always do a BCA table. You always do stoichiometry. No equilibrium when you have strong acids or strong bases in the reaction. Now you can tell that it's a 1-to-1 ratio, and therefore this is a smaller quantity. This is going to go to 0. And this is going to drop down to 0.0040 moles, and then I'm going to end up with 0.001 mole of my conjugate base. Okay, and that would be the outcome of adding that sodium hydroxide. So at the end of this experiment, when I'm finished with this, that hydroxide is gone. So if I go back to listing the species at this point, what species do I have present now? Well, I still have the acid, that's still there. I have the OH minus, which is gone, so that's not there. Sodium ions aren't doing anything, so we don't really care about those. Water is, of course, there, but again, it's not really doing much in this particular problem. And A minus, the conjugate base of that weak acid, is still there. So I still have that conjugate, and then, of course, water. So notice what happened now. It goes back, well, take a look, hold on, before I say it goes back, it's not going back to anything yet. What I have is a weak acid and a conjugate base of that weak acid. What is this? This is your buffer. So what I have is a buffer system at this point. All right. Now what I'm going to do now is I'm going to start using the Henderson Hasselbalch equation. This is going to be a very useful equation. You should have seen this already in a previous video, but I'm going to go ahead and start using this equation because it makes this a lot easier to work with when you're doing the calculations. All right. So I'm going to take pH is equal to pKa plus the log of the base over the acid. Well, I know what my Ka is. My Ka is 1.76 times 10 to the minus 5. And I might not have mentioned this earlier, but that has to be given, and I didn't write it up here in the given information. Since this is a practice problem, we could have looked it up. You can use that to find the pKa, which is the negative log of your Ka, which if you find your pKa would come out to be 4.75. So that's the pH, or the pKa of our Ka. So that's what's going to go in here. So I'm going to go ahead and plug in pH equals 4.75 plus the log of the base, which is my conjugate, right? Which is my conjugate. That's going to be 0.0010 moles over 0.0040 moles on the bottom. Now you're supposed to put concentration in here, but think about it. Your total volume at this point is going to be 50 plus 10, so we have a total of 60 milliliters. You could divide this by 60 and divide this by 60 and plug them into here, but that's going to cancel out because of the division. Alright, so you can plug this in, simplify this, and what you end up with is a pH equal to 4.15. So there's my pH after adding about 10 milliliters of the base. So let's put that on the chart. So my pH at this point is now going up to 4.1. Let's do it in another color. Make it consistent here. 4.15. So when I get to this point around here, let's say that this is the 10 mark. Okay, let's go ahead and put that in as a, well, let's do it in blue to be consistent. All right, so this would be 10 milliliters. At that 10 milliliter mark, I have a pH that has now gone up to about 4.15. Okay. I'm going to continue on. In the next video, what I'll do is I'll do the 25. I'll actually do the last 3 points along this titration curve so you can kind of see how things are playing out. And then in the very last video, I'll talk about looking at this as a whole. All right. So thanks a lot, guys.